Okay, so let's have another example for our beam problem using stiffness method. I have here, I consider this as three-member beam because one of the beam has a different inertia. As you see, it's 1.5 I, while the rest, the two other member, is only 1 I. Okay. Now this is the coding for that. So I subdivided this problem into three member. Okay. So this is the concept, no? So similar to finite element, as I've said always, matrix analysis is already part of a finite element concept, no? Because we're basically subdividing the problem, no, into each member, depending on your discretion as a designer, as an engineer. Here, it's my discretion to put in a code here on here in 2 because there's a changes in inertia. Okay, uh, using classical solution, you can also solve this without indicating another node here or another code for here on this location. But the beauty of finite element or matrix analysis is you can put a code here such that the solution or the output of the problem will generate a displacement on this location, right? And it's also practical to put in a node here in order to come up with a displacement on that point already. Okay, so so in general you can put this infinite, actually, infinite number of code or nodes in this continuous beam. No, that's the general concept. But as an engineer, as a designer, it's wise to put in code or nodes on certain points, like changes in a location where there's a changes in inertia, or say a material, okay, and also loading. You can do that. Okay? So that's the general concept. Anyway, so let's again proceed with the coding here. So 1 and 2, 3 and 4, then 5 and 6, 7 and 8. Okay, so therefore I will need three element stiffness matrices, K1, K2, and K3. And as you notice, since this is only on node 2, this is just a junction at which inertia changes. Therefore, the displacements here, or the degrees of freedom here, will be 2, because on this location, your continuous beam has a vertical displacement, which corresponds to degrees of freedom 3, and it also has a rotation, which corresponds to degrees of freedom 4. Okay, so this is the drawing corresponding to the degrees of freedom or the unknown displacements that we need to get. So therefore we have 3, 4, and then 6 because you have rotation here, and then 8 because you have also rotation here. Okay? So therefore our unknowns is 3, 4, 6, and 8. Okay? Now, therefore your S matrix will correspond to 3, 4, 6, and 8. Okay? So 3, 4, 6, and 8. So that means our expected S matrix is 4 by 4. Okay. Now for each element stiffness matrix, this is the code 1, 2, 3, 4. So we need 3 and 4. For K2, 3, 4, 5, 6. So we need 3, 4, and 6. For K3, we need 6 and 8, right? 6 and 8. Okay. Now, let's set up our BU and BB matrix. So according to my earlier video, BU is the location, right? So what is the location of 3 and 4 in K1? So it's in third and fourth. Okay, so the BU here is sorry, 3 and 4. Okay, what's the location of 3, 4, and 6 in K2? So it's 1, 2, and 4. So this will be 1, okay, 2, and 4. And finally, for K3, its location is 2 and 4, right? So something wrong with my tablet. It's 2 and 4. 2 and 4. Okay, now what will be the destination of this data to our S matrix? So 3, 4 is on first and second, okay? First and second. So this will be on 1 and 2. How about 3, 4, 6? So 3, 4, 6 is first. What's happening? Is first, second, and third. First, second, and third. So first, hey, what's happening? First, second, and third. I'll erase this. First, second, and third. And finally, for 6 and 8, what's the location? It will be on third and fourth. So that will be 3 and 4. Okay, so that will be our BU and BB matrix. Okay, for the QF, okay, referring to this problem, we need about 2 sets of QF. Okay, so say this, consider this as QF1, okay, which corresponds to 1, 2, 3, 4. 1, 2, 3, 4. QF2 corresponds to 3, 4, 5, 6. 3, 4, 5, 6. And finally, QF3 corresponds to 5, 6, 7, 8. 5, 6, 7, 8. Okay, so one is the vertical reaction. So this is my QF1 because this is member 1, this is member 2, and this is member 3. So the fixed end forces. For QF1, I have 63. And then for the moment, it's WL squared over 20. That's the formula. So what's the answer there? 30 times, that is 6 meter. So this is 6 meters. This one is 10 meters. Okay, 10. So W 30 times 6 square divide by 20. I'm getting 54. That is 54. Then vertical reaction is 27. And WL squared over 30 is 36. So this will be negative 36 based on our sign convention. QF2, as you see, there's no loading on QF2. Okay, so this will be all 0. Loading along the member, okay, not on the junction or the end nodes. Next is QF3. We have 150 kilonewton. Based from the formula PL over 8, that is 150 times 10 over 8. What's that moment? 187.5. 187.5. And the reaction is, of course, since this is symmetrical, this is 75. So 187.5. So this is 75. Then 187.5 and another 75 and negative 187.5 kilonewton meter. This is in kilonewton meter. This one is in kilonewton. Okay, so na-set up na natin yun. No? So we've already set up the fixed end forces. Okay. Again, if I rewrite the general formula again, so P minus P sub F is equal to SD. So our PF will be coming from the QFs, okay? While the P load vector will be, again, this is the load vector applied at the nodes, right? So in this case, as you see, we have load forces applied at the nodes. No, this one, the 200 kilonewton and the 90 kilonewton meter. So unlike with the previous example, we don't have the P vector. So what's the P vector now? Okay, so the P load vector is P is equal to, okay, I have, of course, the P should be corresponding to our S, no, which is 3468. So if I set up here, 3468, right, corresponding to the S matrix. So do we have an applied load at degrees of freedom 3? Yes, so that is the 200 kilonewton. So that is the 200 kilonewton. Negative, right? Negative 200. Do we have a load applied at degrees of freedom 4? None, no? It's only a vertical load. So this will be 0. Do we have a load applied at degrees of freedom 6? Yes, that's the 90 kilonewton meter. Okay, so that's the 90 kilonewton meter. 90. Oops, what happened? And finally, do we have a load applied at node degrees of freedom 8? Okay, so none. So this will be 0. Okay. Okay, so based on our, by the way, based on our convention, this should be negative 90. Okay. Remember, on our derivation, or sorry, in our fixed and forces, this is considered positive, while this direction is considered negative. Okay, so this should be negative because 90 is clockwise. Okay, and this one is clockwise. Okay, so how about the PF? What's the final PF vector? So our PF will be coming from the QF. So again, this is corresponding to 3468. Maybe I should enlarge this. 3468. So do we have QF with 3 and all threes, or all corresponding to 3? So this one corresponding to 3. Okay, so it's only 27, right? 27. All QF corresponding to 4. This one, negative 36, and this one. Okay, so this will be negative 36. QF corresponding to 6. This one only, and this one. So that will be 0 plus 187.5. And finally, QF corresponding to 8, have this, which is negative 187.5. Okay, so we now know the P vector, the PF vector, S will be followed, and that's it. We can now find the displacement vector. So let's switch to our SMAT. Okay, so this is our SMAT code. So 1, 2, 3. So our length, I'll change the length as 6 meters. 6, 4, and then here it's 10. So this will be 10. Oops. Okay, how about the inertia? It should be 5.8 times 10 raised to 9. I think this should only be 5.8. I'll check the exponent of our previous problem if consistent with this. Okay, and then inertia, elasticity is only 28 gigapascal, so I'll change this to 28. Okay, so that's it. I can now generate the K1, K2, K3. Oh, by the way, K1 should be 1.5 I. So this should be 1.5. 5.8 times 1.5. 5.8 times 1.5 is 8.7. So it should be 8.7. Okay. And then let's recall our BU. It should be 3, 4, 1, 2, 4, and 2, 4. Okay, this should be 3, 4. So how do I enlarge this this data? So as you notice, if I put in the cursor here, okay, and then press space, there's a symbol that means you can enlarge this matrix, right? Or this submatrix. So I will enlarge this to put in another data. Okay, so that's it. 3, 4, 1, 2, 4, and 2, 4. Space. Okay. 1, 2, 4. Then space here. Then 2, 4. Okay. 3, 4, 1, 2, 4, and 2, 4. And then here 1, 2, 1, 2, 3, and 3, 4. 1, 2, 1, 2, 3. I suggest if I already established the size here, I can just copy this, then paste. Okay. Then 1, 2, 1, 2, 3, 3, 4. 1, 2, 1, 2, 3, 3, 4. Okay. And for the null matrix, our S should be 4 by 4, right? Because it's you have 4 unknowns. So I'll expand this, and then put in zeros here. Okay, then that's it. I can now get my, okay, so as you see, the code becomes red here. That means there's an error. So you need to be consistent. No? So I put in, I loop to 4. Okay, what's the problem here? 1 to 4. 1, 2, 3, 4. Okay. Ah, no, no. It should be 3 because we have 3 elements. Okay, so let's see the. So I found out that there's an error in my null matrix earlier. So I only input 3 by 4. So it should be 4 by 4. No? So there's no more error right now. Okay, in terms of generating the stiffness matrix, the S matrix. So this is the S matrix. Now let's correct the P vector. Okay, so the P vector, it should be 4. And what's the P vector? 27, negative 36. So this should be 27, negative 36, and then 187.5 and negative 187.5. 187.5, negative 187.5. Okay, but remember this formula only uses P. So we should have PF. Still, we also need to have PF. I can just copy this, paste, and I'll assign a new name. So to create a subscript, after P, press in. I'll show you my on-screen keyboard. Okay, so this is my on-screen keyboard. So if you need to put in a subscript, press this button. Okay, and then call this P sub F. Okay. Okay, what's the problem? I think it's syntax incorrect. I'll retype. Okay. Okay. It seems it doesn't want to for now. Maybe there's another variable using the same PF. Okay. Sorry. I can only PF. Maybe this one is already okay. But if I put in a subscript number, okay, no error. It only wants a subscript number. Okay. Okay. PF. This one is okay. Now, what's our PF as we solved earlier? Oh, 200 negative 90 pala yung ano. Sorry. So this is the PF. The P vector should be 200 negative 200. Sorry. It should be negative 200. Then negative 90. Then 0. PF is already good. It's already okay. This one. And P should be this. Okay. Then let's find the P minus PF. Maybe I can reassign this as what? maybe PL. That means load vector. Okay. So that I can reassign the variable P as PL minus PF. Okay. So that's it. It's already good. Okay. So this now is P minus PF, which is this. Okay, so remember our equation is P minus PF is equal to ST. So I'll rewrite this as P. Okay. Therefore, D is equal to S inverse P, which is this. So this is our displacement. So which corresponds to 3, 4, 6, 8. So that means this is a vertical displacement. This is the rotation, rotation and rotation. Okay. So let's verify that in STAAD. And also, our U1 is, remember, we are fixed connected on member 1. So therefore, this is correct, 0, 0. Now, this will now be D1 and this will be D2. Okay. This will be here. This will be this. Okay. So I'll retype this. This will be D1. This will be D2. For U2, okay, this one, for U2, we have D1 here, D2 here, and yeah, 0, and this should be D3. Okay. Control C. This will be D2. This will be D3. Finally, for D3, so it's, we have, yeah, 0, and then this should be D3, and then we have D4 here. So D3, D4. Control B. Okay, that's it. And then QF1, I'll update the QF1. 63, 54, 27, negative 3, 36. It should be 63, 4, 36. K1, U1 plus QF1. Okay, and then for QF2, yeah, it's 0. K2U2 plus QF2. And fine. Q3, update the QF3, should be 75, 187.5. Should be 187.5. Okay. Okay, and then, okay, so referring to this drawing, I need a 28 gigapascal material. So this is my STAAD model. I'll create a new material out of steel. For example, I'll create. So I'll drop down, choose steel, or say I'll retype this to create a new material. 28 gigapascal. So this is 205, 2.05, 205, but I only need 28. So that will be 0.28, 205. Yeah, 0.28, 0.28. And then, yeah, this is already good. Okay, and then assign to our uh, members. So again, my combo number 2, select the command and then select the objects or geometry. Okay, then assign. Next is properties. I need a 5.8 times 10 raised to 9 millimeter to the 4th. 5.8 times 10 raised to 9. Okay, millimeters to the 4th. So assuming I have 300 by h. So that is bh cubed over 12 is equal to 300 h cubed over 12. What will be my h? 10 raised to 9 times 12 divide 300, then cube root. Getting 614.46. 614.46. And to get a 1.5i, I'll simply need to multiply the 300 by 1.5. So this will be this. For the 1.5i, the section is only 450. And the height is this. Okay. 614.46. So I'll change this. I'll choose our new material. Z is 0.3, 0.61446. And then assign. Okay. And create a new one. Make this 0.45446. Okay. 0.45 and 6.61446, then add. And this is the 1.5i, remember? So I'll select the command, select this object, and then assign. Now maybe if I 3D render, right click 3D render. What's the so here is it. So we should get a larger cross section because it's 1.5i. The rest is I. Okay, so close this. For the supports, yeah. So fixed butt on this two nodes here because they will allow rotation but no vertical displacement. And fixed here, okay. For the loading, okay, expand this. So this is the 150 kilonewton, 200 kilonewton is here. Moment 90, I cannot see here. Maybe when applied later, or I can just scale the loading diagram. And for the 30 kilonewton meter triangular load, this is our loading. And that's it. We can analyze this already. Okay, and then run analysis. Okay, so no errors. And click done. Let's find our supports reaction. Post-processing. Then okay. So here's our data. So according here, I got a vertical 6.5 over here. Okay, 6.5 mm. What do we got on our SMAT? Our displacement is 4.47. There's a discrepancy. Let's verify. Okay, so I verified the model earlier. I should have put in a negative sign in our moment. It should be negative 90 instead of positive 90. And that's after running. So this is our new result. Okay, so we have 4.5 vertical displacement on node 2, which is, I already pasted the values in, which is almost the same to our vertical displacements here, 4.47. Okay. For the rotation, I don't know if it's should be in radian. Okay. So this is already too small. Okay. Let's proceed with vertical reaction instead. So if I interpret this member n forces in our SMAT, this will be that. So I have 146 and a moment of 281. Here I have negative 56 and a moment of 236. For member 2, I have negative 143 and a moment of negative 236. So as you see, negative 236. So that will cancel out this moment here. Okay. And 143 as a reaction and a moment of 337. Negative 337, this one. For member 3, I have 99.79 and a moment of 247. Okay. 247. And 50 as reaction. in 0 moment. I no longer add the decimal digits. Okay, so let's check with STAAD. Our reaction here is 146 and 281. So as you see, click on reaction, and these are the corresponding forces and moment. Okay, so on node 1, we have vertical reaction 146 and 281. Okay, which is the same with our SMAT solution. Okay, how do we reconcile that? I'll okay. Click on annotate, remove all, no? To remove all the reactions. Then Shift S to display all the node numbers. Okay. Right click structure diagram. I don't want to see the sections, so click on none, labels, and then none, apply. Okay, I just wanted to see the node numbers so I can verify with result. Put in here, and I paste this. Oops. Okay, so again, if you wanted to see all the nodes only, so under the post-processing reactions, click on annotate and then remove all. And then Shift N for display of nodes. So Shift N. Okay. And then Shift S to enable or disable the supports. So I captured this and I paste it here. Then for the beam results, to get the member forces, this is my, so click on beam results, and then by default you will see the moment diagram MZ, because remember you have a global displacement axis and also a local axis, right? So your local axis, so this is local Z, this is local Y, therefore moment about this axis is mz, and then force parallel to the y-axis is Fy, and then this is x, so force along the longitudinal axis is Fx. So the moment, the bending moment is mz, the shear is Fy, and then the axial is Fx. Okay, and by default you shown here is mz, and these are the member forces, again referred to the local axis. So I put them here. So after translating after reflecting these forces here, let's check with STAAD. So node 1, our reaction is 146, 146, and 281. 281. For node 3, because that's the location of supports here, the reaction is 243. So if you add up 143 plus 99.8, that's almost 243. And no moment. Okay. Remember here, you have negative 337 and 247. they didn't cancel out because remember we have an applied moment of 90. So that will cancel out. That will make this joint with zero moment. Okay, so 247 plus 90 is 337. Okay, and finally for node 4, this one, that's 50 kilonewton. 50.0203, no? Just this. Okay, how about for member forces? Let's check the consistency. Okay, so member 1, we have 146 and 281. That's one. And node 2, we have 56 and 236. 56, 236. Member 2, node 2, 143, 236. 143, 236. And 143, 337. 143, 337. 99, 247. 99 to 47 and 50 0. 50 0. Okay, so that means this is consistent with our STAAD model and our SMAT code. Okay, so again, you can do this in Excel, but you will realize that as the member goes, uh, your displacements becomes more. You have your S matrix will become larger. Okay, and it's a tedious process, so you need a code to quickly generate the structure stiffness matrix, as I did here in our SMAT code.